Hello again. Last time we looked at vector norms and how that can quantify the size of a vector using different definitions. This time we're going to do the equivalent now for a matrix, and that's all about trying to collapse a matrix down to a vector and apply a similar procedure as we did before. We're also going to give a couple of important identities for using matrices, and then we're in a position then finally to look at the convergence rate of Jacobi method, and that's what we'll start to do in this and then the next lecture. So last time we looked at vector norms, and now we're moving on to matrix norms, which are highly related. And then we've got all our tools for doing a convergence analysis of this important matrix inversion problem. So given matrix A, which we're considering, the infinity norm is defined as, so two vertical bars subscript infinity as the max over I equals 1. Yes, I saw this is a little typo in the lecture notes. This I equals 1 to n should be included in this definition. So where I, J are the components in row column format of your matrix A. So this looks complicated at the moment, but we'll unpack that with some examples. But what we're doing is very similar to the matrix definition. So the vector definition. The vector definition had max I is 1 to n. So that was basically going over all the components of your vector, find the maximum absolute value, and you've got the absolute value here. So the extra bit that's really to do with the matrix bit is this summation. So this summation over J. So this is a summation a lot across over columns, yeah. Summation of J. So the second element is the column element of J. So we're going to over columns or along rows. Okay, it's the same thing, whichever you prefer. Your summation across columns or along rows, exactly the same thing of all the elements. So basically what we've done first here in this expression is summation across these column values to make it into a vector if it's a 2 by 2 case, and then you apply the same rule as you had for vectors. So that's what I mean, it's highly related. Right, so that's sort of a little bit abstract because that's the full expression. Now let's just do a 2 by 2 matrix to make it a little bit more concrete. So consider a 2 by 2 matrix. So I think this matrix, the sort of theory, the matrix is in terms of all these vectors, norms and decompositions can seem a little bit abstract at times, but if it is, I always recommend searching out, or if it's not in my notes, a 2 by 2 example that you can really understand and give you sort of concrete examples. So here's a 2 by 2 example of doing a a matrix norm. So if A is just 1 minus 2, 3, 4, then the L infinity norm is simply and I'm just going to break it into 2 lines actually. What is just so it's obvious. So we're gonna basically sum along rows the absolute values. That's row 1. Yeah. So we're summing the absolute values along there and making those into a vector, and then summing the row 2. Like that. So that's row 2. Row 2. So the first thing is we're just converting this 2 by 2 matrix into a vector problem. So we take the absolute values of each thing, add them together, and then we've got something very equivalent to our matrix sample. So that means that then we've got a maximum of 2 values, which is just 3 and 7, which equals 7. So easy. Okay. So often with the absolute values, you had some sort of identities that you either state or you implicitly use when you're doing that. But it's useful before we proceed a little bit further. We just state a very useful. So these 4 norms. There's 2 useful identities that come in. We're not going to prove them, but we're going to state them. So recall for 2 scalars, A comma B, that if you have the modulus of the product, that's identical to the product of moduluses. And you may not have called it this, but this is called multiplicativity. This is where we're going to get a bit tongue-tied, I'm afraid. Multiplicativity. Okay, so this is multiplicativity. For scalars we have that identity. So the question is there an equivalent for matrices? And it turns out there is. So for 2 matrices, A and B, so if we have the product and we take the norm, how is that related to the product of the norms? Okay, so before, remember the scalar example, we just had norms. Now we have full vectors, so full matrices. So it's no surprise it's not the same, exactly the same. It actually changes from an identity to an inequality. So maybe I should have called this inequalities for matrices, but you get the idea. And it turns out that it's actually less than equal. That's the state we can say. So it turns out that it's a form of multiplicativity it's actually sub-multiplicativity. And if you can say that after a few drinks, then you're doing very well. There's a simpler phrase, I don't know. that's it. So basically saying that the norm of the product, but this is very useful because it will, wherever we've got a product of two matrices and we take the norms, we can break them apart into their component norms, and that's going to be very useful for our proofs. So we're going to use that rule. And there's a similar relation exists when multiplying matrix and vector. So if we take AX, the left hand side, so matrix times a vector, and now we take the norm of that, again that can be broken up into the norm of A times the norm of X. Notice I haven't specified which norm here. It applies to all. Okay, so it could be infinity, it could be 2, and equivalently there. So I don't know if this gets proved anywhere in pure modules in here. There is a proof out there, but this is an applied course. We tend to prove what I consider our very key results that are within the grasp of our level of mathematics. So I won't prove these, but I'll just state them without proof. But there are proofs out there if you're interested. Okay. All right, so those are the useful things. So we've got a definition of a norm for matrix, and we've got our sub-multiplicativity rules. So we've got just under 10 minutes to now bring everything together. So this is the bit you've all been waiting for, the exciting bit where we bring together all the tools we've got. So we've let's just recall. We've expressed B matrix, so that we're looking at methods that are iterative methods of the form xn, and there we go. C minus B of x of n, yeah, and we express B matrix in terms of these matrices L, D, and U. That's the first thing we did. Then we defined norms of matrices and vectors, and then quantities. So those are the two tools we're bringing forward now into our analysis of convergence. So it turns out for Jacobi and Gauss-Seidel, it's the B matrix that is key to understanding convergence. Okay, so B matrix is converted. So it turns out the B matrix is key to understanding convergence. If you're interested in analogies with the root finding part of the module, the root finding part of the module fixed, this is analogous to fixed point method here. We looked at G prime, yeah, and you've got that in your coursework, is key to convergence. Well, this is the analogous result for Jacobi. So let's see how it all works. So I'm just going to start this in this video and then obviously carry it on. So this is possibly the most analytical part of this module, and then let's get more practical. It certainly gets more practical into term 2 again. We're interested in convergence analysis of Jacobi and also comparing Jacobi and Gauss-Seidel. So I'm going to actually show you two approaches to convergence analysis. So the first one I call in the lecture notes the method of norms, because we use our norms that we've previously defined. And this is probably the most rigorous and complete way of doing convergence analysis, but it's also probably most cumbersome way as well. So I'm going to show you sort of the sort of most rigorous method first, and then show you actually a very convenient calculation using eigenvalues, a spectral method it's called, that will actually allow us to compare Jacobi and Gauss-Seidel. So we're going to look at convergence Jacobi, and then we're going to use a simpler method for comparing the speed of convergence of Jacobi and Gauss-Seidel. Okay. So let's start with some definitions. So definition 3 in the lecture notes, but and this is diagonal dominance. So remember, we're underlying this. We're solving the problem AX equals B. Yeah. As we're solving AX equals B by defining a different matrix, a related matrix to AB called B, which allows us to iterate. But we're still always solving AX equals B. That's the underlying problem. Important to remember that. So definition: diagonal dominance. A is strictly diagonally dominant if, now little a is its components, yeah, AII is greater than sum j not equal to I where Aij are elements of A. Again, we've written it down in probably the most abstract form, but we'll give examples. What we've got here, actually, if we just look at it, these are going to be your diagonal elements. And these, because we've set up a summation where, so these are again summing the long rows where j not, these are off diagonal. I'll give an example of this in a minute. We've got the diagonal elements and off diagonal elements. And we've got the absolute values. And actually we've got this thing strictly, and strictly comes due to this greater than. Okay, so you can have some situations where this is a greater than equal to, but the strictly bit comes into there. So although this may still need an example to show you, just pointing to the various aspects. We've got the diagonal elements greater than the sum of the off diagonal elements for each value of I. So let's give an example of this, because that's yeah. And I'll just give an example of this diagonal dominance now, and then we finish. So if we have a matrix 5, 2, 1, 0, 4, minus 3, minus 4, 2, 7. Let's just look at row 1. Diagonal element which is A1, 1 is 5. The sum of the off diagonals absoluted is A 1, 2 plus A 1, 3, which is 2 plus 1, which equals 3. So, and 5 is greater than 3 implies that row 1 satisfies inequality. And then basically repeat for rows 2, 3. So row 2 here, we have absolute value of 4 is greater than 3, that's fine. And then here we have the diagonal element 7 is greater than 4 plus 2. So this means that this matrix is diagonally dominant. Tick. Yeah, so we're going through all the same, we're going through all the diagonal elements and saying whether it's greater than the sum of the off diagonal elements. So 5 is greater than 2 plus 1, 4 is greater than 3, and 7 is greater than 4 plus 2. So this is actually very straightforward calculation when you see it written out like that, but when you see it, the inequality written in component forms, it looks a little bit abstract, but that's, again, decoding it with a real example always helps. Okay, I'm going to pause there and we'll carry on with our analysis of convergence of Jacobi method next time.